Welcome to an example on how to determine volume by slices, integrating with respect to y. A volume is described as follows. The base is the region bounded by x equals negative y squared plus 14y plus 3, and x equals y squared minus 26y plus 185. Notice I've already graphed the bounded region on the graph below. Every cross-section is perpendicular to the y-axis and is a semicircle. I've also shown two slices of the solid, which we can see are semicircles. So first, notice how the bounded region is bounded on the right by the curve given by x equals negative y squared plus 14y plus 3. And therefore, let's label this x sub r. And the bounded region is bounded on the left by x equals y squared minus 26y plus 185. Let's label this r sub l. The volume of the solid is equal to the integral from c to d of a of y differential y, where a of y is the area of one slice of the solid. Notice here, we're integrating with respect to y because each cross-section is perpendicular to the y-axis and we are given functions of y. Again, looking at the bounded region, this means the limits of integration will be from y equals 7 to y equals 13. We will verify this algebraically shortly. But to begin, let's work on determining a of y, which should be the area of one slice of the solid. And since each slice or cross-section is a semicircle, a of y is equal to half the area of a circle, which is 1/2 pi r squared, where r is equal to half the length of x sub r minus x sub l, where x sub r is the function on the right and x sub l is the function on the left. So let's work on determining r on the next slide. Again, the radius is equal to half the length of the quantity x sub r minus x sub l, which is equal to 1/2 times the difference of the quantity negative y squared plus 14y plus 3 and y squared minus 26y plus 185. So simplifying inside the parentheses, we have 1/2 times the quantity negative 2y squared plus 40y minus 182. Distributing the 1/2 gives us the radius, which is equal to negative y squared plus 20y minus 91, which means a of y is equal to 1/2 times pi times the square of negative y plus 20y minus 91. This is the integrand function for the integral that will give us the volume of the solid. And because we're integrating with respect to y, we would have to find the y coordinates of the points of intersection, which I've shown below, by setting the two functions equal to each other and solving for y, which we can see give us y equals 7 as well as y equals 13, which again will be the limits of integration. So to set this up, the volume is equal to the integral from 7 to 13 of a of y, which is 1/2 pi times the square of the quantity negative y squared plus 20y minus 91, and we're integrating with respect to y. So we still have quite a bit of work here. We now have to square negative y squared plus 20y minus 91. Let's work on this on the next slide. Let's go ahead and factor out the 1/2 pi. And then the square of the quantity negative y squared plus 20y minus 91 is equal to y to the 4th minus 40y cubed plus 582y squared minus 3,640y plus 8,281. And now we need to find the antiderivative, which is y to the 5th divided by 5 minus 40 times y to the 4th divided by 4, or minus 40 divided by 4 y to the 4th, plus 582 times y cubed divided by 3, or plus 582 divided by 3 y cubed, minus 3,640 times y squared divided by 2, or minus 3,640 divided by 2 times y squared, and then plus 8,281y. Next, we have 1/2 pi times big F of 13 minus big F of 7 To find big F of 13, we substitute 13 for y. To find big F of 7, we substitute 7 for y. And I've already done this to save some time. We have 1/2 pi times the quantity 74,698 fifths minus 73,402 fifths. So 1/2 pi times this difference comes out to exactly 648 fifths pi, which is approximately 407.1504, which is equal to the volume we are looking for. I hope you found this helpful.